The purpose of this video is to, in general, solve the tangent line problem for a curve given in parametric form. In other words, we want the slope of the tangent line at a particular point. Then we're going to apply it to this example where I have a pretty complicated parametric curve. It's called a cycloid, and you'll see what it looks like when we use the graphing software to plot it. And we're going to get the slope at a particular value of t, and then we're going to use that to find the equation of the tangent line and overlay it on the plot to make sure it touches at exactly 1 point like a tangent line should. So it turns out deriving the calculus here is pretty fast. What's the slope of the tangent line? It's dy dx. But I could rewrite that as dy dt over dx dt. And that's just y prime of t, the derivative of y with respect to the parameter t, divided by x prime of t. Again, our curve being given by a pair of parametric equations generating the x and y coordinates as a function of t. So let's take a look at this cycloid. And an interesting thing about this curve, it's exactly what would be traced out if you painted a spot right at the rim of a rolling wheel. The section of the cycloid that I plotted here starts at t equals 0 and ends at t equals 4 pi. And maybe we should start by finding the point on the curve corresponding to t equals pi. That's the moment of interest here. So x of pi is going to be pi minus 2 sine pi over 2. Sine pi over 2 is 1, so I end up with pi minus 2. So pi is a little bigger than 3. Take away 2 from it, you get something a little bigger than 1. So I'm somewhere over here in my x coordinate. Let's take a look at y of pi. That's going to be 2 minus 2 cosine pi over 2, but cosine pi over 2 is 0. So y is going to be equal to 2. So it looks like I'm right here on the curve, and I'm trying to generate the tangent line to this thing. I'll need this later, so I'm just going to write down the point as an ordered pair. That's pi minus 2, comma 2. All right, then we use our simple formula for the slope of a parametric curve. So first we'll do the derivative of y, and it has a constant as its first term, so that's gone. And then the derivative of cosine gives me negative sine, which makes the second term positive. So I have a 2 sine of t over 2. Tack on the 1/2 from the chain rule, that's from differentiating t over 2 with respect to t. The 1/2 and the 2 cancel, and I get sine of t over 2. All right, this means y prime at the point of interest, which is pi, is the sine of pi over 2, in other words, 1. Next, we check out x prime of t. And when I differentiate the t, I get a 1 minus 2 cosine t over 2. And again, the chain rule produces a 1/2 now from differentiating t over 2. And the 2 and the 1/2 cancel out. And I get, in general, that x prime of t is 1 minus cosine t over 2. But specifically to the point of interest, x prime of pi is 1 minus the cosine of pi over 2, which again just gives me 1. So that's simple enough. My slope at t equals pi is going to be 1 over 1. In other words, it's just 1. So now I have the point this line is passing through, and I have the slope of the line. And I just plug into the point slope formula, and that gives me y minus 2 equals 1 times the quantity x minus pi minus 2. I'm going to clean this up and solve for y so I can input it in my plotting software. So I distribute the negative 1 across the pi minus 2 and then add 2 to both sides. And I've got something ready for my plotting software in Slope-Intercept Form. And finally, we plot the tangent line together with the cycloid curve. And the plot looks pretty convincing that this is actually the tangent line at the point of interest.